Hi, I'm Daniel, and today we are going to discuss the fundamentals of the oxycombustion process and its relevance for the enhanced CO2 capture. Let's introduce first the difference between the air-blown combustion and the oxycombustion. Also, we are going to show some of the equations that govern the modeling and simulation of the oxycombustion process. We are going to describe some of the auxiliary systems that are required to run the oxycombustion process. And finally, we will show some examples of process integration in the combined heat and power generation systems, such as in the Allen cycle, as well in the very high temperature heat supply industries, like in the aluminum remelting, the steel, and the glass production. Let's start introducing what is oxycombustion and what is important. You know that the traditional combustion uses air, that is around 78% nitrogen, 21% oxygen, and the rest some gases like argon. And in this traditional combustion, the nitrogen that is in the air dilutes the flame energy and also reduces the concentration of the CO2 in the flue gases. Meanwhile, in the oxycombustion process, we use pure oxygen to burn the fuel instead of air. If you see the figure that we have here below, when we use plain air, this air-blown combustion produces a flame that it has a lower temperature, as we are going to discuss it later. But if we use directly oxygen without the presence of nitrogen, then we can achieve what is called oxycombustion flame, that it has better properties and higher temperatures. If we decide to have something in between of these two options, such as the combustion with oxygen and air mixture, we can have what is called an enriched air combustion. So why do we use oxycombustion? It has higher flame temperatures that are very useful in some applications like aluminum remelting, glass production, and steel production. It has higher energy density and combustion efficiency because we are not diluting the flue gases with nitrogen. But there is one characteristic that is very important about oxycombustion, especially in the case of the energy transition and decarbonization strategies, and is that it makes easier the CO2 capture and separation. We say that the oxycombustion flue gases are mainly composed of water and CO2. Then if we can condense out this water, the CO2 can be separated, treated, and then used in other applications or in permanent sequestration. If we compare the oxycombustion with the post-combustion carbon capture, this later one, it requires the use of chemical solvents that also consume a lot of steam for regenerating the solvent and releasing back the CO2. Oxycombustion has several benefits, but also challenges. Among the advantages, we know that it reduces the nitrogen dilution, so there are less stack losses. It also produces a CO2-rich exhaust gas that enables an effective carbon capture. It has a higher heating rate, therefore it reduces the fuel consumption, but it has an initial investment for the air separation unit and the changing of the burners, and also an additional energy consumption for producing the oxygen. It may also suffer from false air leakage. In this case, the nitrogen that enters with air can dilute the flue stack gases, and in the worst case, it can even produce nitrogen oxides. And also, we have some burner material issues because of the higher flame temperatures. Among those applications that we mentioned, there are also the metal cutting and welding. You have heard about the oxy-acetylene torch, the cement and glass manufacturing because they require high temperatures, but they also produce a lot of CO2, the waste incineration, and as mentioned before, the CO2 capture. Now, let's discuss the governing equations that we use to simulate the air-blown and the oxycombustion processes. You see that differently from the air-blown combustion, the oxycombustion processes does not have nitrogen in the flue gases. For this reason, the air-fuel combustion yields lower flame temperature and also a very low concentration of CO2 in the flue gas. Moreover, due to the presence of nitrogen and the high temperatures of the combustion, we can have a probability of producing nitrogen oxides. In the case of the oxy-fuel combustion, the higher flame temperature and the increased CO2 concentration, together with the low concentration of nitrogen, reduces the amount of nitrogen oxides produced. You can see here in the left that for a temperature of operation of the chamber of around 400 degrees Celsius, the consumption of fuel in the air-blown combustion is around 50% higher than if you compare it with the oxy-combustion. Also, the flue gas flow rate in the case of the air-blown combustion is around 4 times higher compared to the flow rate of the flue gas in the oxycombustion application. The characteristics of the flue gases are also different. The CP of the flue gas is around 1.2 kilojoule per kilogram Kelvin in the case of the air-blown combustion, compared to the 1.8 kilojoule per kilogram in the case of the oxycombustion. Therefore, the air-blown combustion produces an adiabatic flame temperature that is much lower than the oxy-combustion process. If we compare the two tables at the left, the complete combustion and the equilibrium combustion of methane in air, the adiabatic flame temperature is around 2300 kelvins. You can compare it with the values that are estimated for the complete combustion or the equilibrium combustion for the oxy-combustion that are around 3000 and maximum 5000 Kelvin. In order to simulate the oxy-combustion furnaces, we require a couple of parameters, such as the adiabatic flame temperature, that is dependent on the fuel and if we are using oxygen or air for the combustion, the reference temperature of the environment, the radiation temperature, that is a threshold of temperature in which we consider that the radiation has a larger influence as mechanism for heat transfer, the roof temperature, that is the average temperature of the chamber, the stack temperature, that is the temperature at which we finally release the flue gases to the environment, the recycling temperature, that is the temperature at which we can send back part of the CO2 that has been captured or the flue gases to control the temperature in the chamber, and the wall and the loss temperatures that are associated to the heat losses through the walls and the hot air escaping. We also need to know which is the molecular weight of the oxygen, the fuel, and the CO2, and the lower heating value of my fuel. Other characteristics that are more associated to the stoichiometry of the fuel combustion are the molar oxygen to fuel ratio, as well as the excess oxygen ratio. We have the heating capacities of the oxygen, the natural gas, and the CO2 in the flue gas, and the temperature of preheating if we are going to preheat the air and the oxygen that is incoming to my furnace. We have the recycling factors and the wall loss factor and hot gas factor that are associated to these losses that we mentioned before. Here we have a representation of the cooling of the flue gases that can be used as an equivalent representation for my oxy-combustion furnace. You can see that in the y-axis, we have the temperature levels, and in the x-axis, we have the heat. The heat is dependent on the lower heating value of the fuel and the flow rate of the fuel. You can also see that here, all of the temperature levels, the adiabatic temperature flame, the radiation temperature, the roof temperature, the stack temperature, and the environment temperature are shown. From this diagram, it's possible to see how much heat is available above the roof temperature, which is useful for heating my load in the combustion chamber. There is another amount of heat that is available below the roof temperature, that is after it leaves the combustion chamber, and can be used to preheat the oxygen that enters the combustion chamber or for cogeneration purposes. We can even try to go to the ambient temperature and further cool down the stack gases. But then we will require specialized heat exchangers to ensure the corrosive conditions. It's also interesting to see that all of the external waste heat that is available, it can be either used for preheating the load that goes into the combustion chamber, but it's better if we use it to preheat the combustion air. This is because all of the energy that is recovered by preheating the combustion air can be pumped up above the adiabatic temperature flame, as it can be seen here. Another interesting detail here is that if we increase the amount of recirculation of flue gas or CO2, the adiabatic temperature flame drops because we are injecting an inert gas that is going to decrease the slope, which is related to the CP of the flue gases. This formula allows us to calculate the adiabatic flame temperature that has been corrected after we consider the excess of oxygen and the recirculation ratio of the flue gas. The CP corrected is calculated based on this adiabatic flame temperature. The amount of oxygen can be calculated based on the fuel and the excess oxygen consumption. The total demand of heat can be calculated based on the useful load, but also on the furnace wall losses and the hot air escaping. The CO2 emissions can be divided into the captured CO2 and the emitted CO2. Let's talk about the auxiliary system that allows to operate the oxycombustion processes. Those auxiliary systems mainly consist of the air separation unit, the waste heat recovery and condensation units. The air separation unit can be a cryogenic distillation technology, a pressure swing absorption technology, or a membrane separation technology. Those technologies produce the oxygen that is used in the combustion chamber. They also produce as a byproduct atmospheric nitrogen. After the waste heat recovery, the flue gases are cooled and separated in a condensation process where the CO2 is the gas is separated and further treated in the carbon purification unit. The CO2 can be also recirculated in order to control the temperature of the oxycombustion furnaces. The air separation unit is responsible for producing the oxygen that is used in the oxycombustion processes. In the case of the cryogenic air separation unit, the oxygen is separated from the nitrogen thanks to the different boiling points. In this system, the air is compressed to around 7 bars and then is fed to thermally integrated distillation columns that achieve an oxygen purity of 99%. In the case of the pressure swing absorption unit, the pressurized air is fed to absorbent-containing beds that selectively they absorb the nitrogen. Once the bed is saturated with nitrogen, it is regenerated by depressurizing the bed, and then it releases the nitrogen, restarting the cycle of air separation. After the non-recirculated CO2 gas is cleaned in particles and sulfur, is dried and then sent to a compression and purification unit. In this unit, a high-purity CO2 stream is produced that is suitable for use and transportation. As you can see, the flue gas with a high concentration of CO2 because the water has been condensed out in the waste heat recovery train. The CO2 is sent to a molecular sieve that dries the CO2 and then is cooled down in a cold box using the returning streams that cool down the CO2 to a temperature level that is liquid and then is regasified and compressed. The other streams that appear here are basically recirculation streams that also leverage a membrane system to increase the CO2 recovery. Let's talk about the process integration of the oxycombustion furnaces in the industry. One of those applications is the alarm cycle, in which a certain amount of oxygen is produced in an air separation unit so that the oxygen can be mixed together with the fuel, in this case natural gas, in the combustion chamber, along with the recirculated flue gases. In this chamber is produced a very high pressure and temperature gas that is expanded in a turbine. The hot gases are cooled down by preheating the recirculated flue gases. In this way, a very efficient power generation system can be operated, as you can see here in the composite curves. This power that is generated in the cycle is used to drive the compressors of a petroleum platform. As you can see, the CO2 that is separated in the alarm cycle can be compressed and then reinjected to reduce the impact of the petroleum production facilities. Another application in the industry is the melting of metal and glass. Due to the high temperatures required in the melting of these materials, normally above the 1000 or 1600 degrees, Linde, Air Liquide, and Nippon Gas have already developed some oxycombustion furnaces that can be readily applied into the melting applications of the aluminum and glass sectors. With this, we finalize this introduction to the oxycombustion processes. We learned that the oxycombustion allows us to achieve very high temperatures with also very high efficiency, which is important for some applications that are very difficult to electrify. Also, we learned that the oxycombustion allows us to separate in an easier way the CO2 out from the water if you compare it with the normal air-blown combustion. There are some challenges still related to the leakage of nitrogen into the furnace, which can cause maybe some nitrogen oxides emissions, but with the right control of the furnace pressures, as well as trying to improve the furnace recirculation, we can make this oxycombustion application one of the key implementations for driving the energy transition and decarbonizing the hard-to-abate and high-temperature heat supply in the industrial sectors.